at refraction seismology. Now, we initially thought that when there is seismic wave incidenting at a boundary, there are some possibilities that one, the waves will be reflected or it will be what? Refracted. Now, in terms of reflection, means that it will occur within the same media. And so we are going to have our angle of incidence to be equal to our angle of reflection. But in situation where it is refracted, so this media, the velocity of the seismic wave, let's consider it to be V1 in this media, and this medium to be V2. You get it? Now, in situation where V1 is greater than what? V2, meaning that this is denser. This is denser than this side. So this is less dense. In that case, the refracted ray will move towards the refracted ray, and the normal circumstance is the original path of the ray. So it will move towards the normal. So this is our normal. You get it? Now, in situations where V2 is greater than V1, meaning that this is less dense and this is for denser. Now, here we are looking at seismic waves. Remember that Vp is equal to square root of what? K plus 4 on 3 mu all over what? Rho. And we said that as density increases, the velocity and primary velocity of the seismic the primary velocity of the seismic waves will increase. So if you are using the analogy for light, it's different here. Here, know that as density increases, your velocity will increase. So in the first scenario I gave, where V1 is greater than V2, means that this layer is denser than what? This layer. Do you get it? And so in that case, the velocity here will be greater. And so when the seismic waves gets into this media, it will move towards the normal. But in situation where V2 is greater than V1, V2 is greater than V1, let me erase this. So when we have V2 being greater than V1, it means that the layer that V2 is in is denser. So it means that this layer is dense than what? This layer. So this layer is what? Less dense. So in that case, less dense. So in that case, what will happen? The refracted ray will move away from the normal because now the wave is moving with a higher what? Velocity. So it will move away from the normal. And that is what we are going to import in this side. So in exploration geophysics, where we want to explore, let's say, what is within subsurface, we can deploy the use of the seismic wave, that is the refraction seismology. So assuming we have this to be our focus, this to be a geophone, you get it. Now, when we apply, let's say, we induce the geophone to produce the seismic waves, right? So we are going to have, let's assume there's going to be our incident. Let me erase this to make it much clearer. That's going to be our incidence. So we are going to take into consideration the three possibilities. So if this is our incidence, then we can have what? A reflection. So assuming the geophone is here, we can have a reflection. In another situation, we can have this to be our incidence. Then we will have, remember, the when the incidence ray is is done critically. So there's going to be the refracted ray along the boundary. So this is the refracted ray along the boundary. Then it will get reflected back. You get it. Then we can have the direct. So let me use another color for the direct. Let me use the blue color for the direct. So there are three possibilities. So this is the first one. So this one is normal reflection, and this one is refraction. Now, in the first scenario, let's take the first scenario of reflection, the first scenario of reflection. Oh, these diagrams that I'm drawing. So if we consider the first layer of reflection, uh, so for reflection, this is how it's going to be, right? Now, assuming from here to here is a certain distance x, right? This is going to be our normal. We are taking the reflection. So this is going to be our normal. So it means that this is going to be in half x, half of what? X, right? Now, what is this? So we are trying to determine which of these waves will get to our geophone. So this is like our geophone. Which of these waves will get to our geophones earlier? So we are going to first of all, there is the direct wave. This is the direct wave with reflected, the one creating reflected. Then this is for the refracted. So we have three conditions: the direct wave, reflected wave, and the. So we are going to compare the direct wave and the what reflected what wave. Which of them will get to the geophone early? So let's take now for the direct wave is within medium one, this medium, and so the velocity there will be what v1, and here the velocity here will be v2, right? So we want to know the time there. So what we are actually doing is we want to find the first arrival. Which of these waves will get to the geophones first? So under the direct wave, so let me see direct here. Let me let me see direct wave here. So direct wave. So under the direct wave, we are seeing that T1 is equal to the distance traveled by divided by the velocity. So the distance traveled is what? From FD, that is from the focus to the geophones, divided by what? V1. Do you get it? Now, what is FD? FD, we said that is X over what? V1. Now, let's look at um, the reflected wave. So the reflected wave. So the reflected wave, let's say the time that wave gets to the geophone is T2. You get it? Now, what will it be? It's going to be Fe divided by V1. They are in the same material, so V1, the same velocity, plus what? EB over what? V1. You get it? But if you look carefully, because it is reflection, we will know that Fe is what? Is equal to what? Ed. So I can say that T2 is equal to what? 2Fe over what? V1. Do you get it? Now, when you bring the reflected ray out, when you bring it out, this is how it look like this, with the normal being here. Now, the normal divides this side into two equal halves. So this is 1 over x, 1 over 2x, 1 over 2x, right? Now, we want to know the distance. Let's say from here to here is a certain height, h. So here is h. We want to know the distance from here to here. You get it? Now we've established that Fe, that is from here to here, is the same as from here to here, is the same as from here to here. And so that's why we have this equation. But we want to know this distance. So we can see that it's a right angle triangle, right? So knowing that it's a right angle triangle, we can see that this side, that is FE squared, is equal to what? H squared plus 1 over 2 x all squared, right? And so I can see that FE squared is equal to H squared plus what? 1 over 4 x squared. You can see that it's a right angle triangle. So if we continue, with this, we are going to get what? If we continue with it, we are going to get FE squared to be equal to 4 squared plus what? Plus x squared all over what? 4. So if I want to make FE the subject, it's going to be square root of what? This entire expression, 4 squared plus x squared over what? 4. So I can say that FE is equal to what? 1 over 2 square root of what? 4 squared plus what? X squared. Now we can put this into this equation, right? So I can say that T2 is equal to what? 2 multiplying the expression 1 over 2 multiplying what? 4 squared plus what? X squared over what? V1. I can see that T2 is equal to square root of what? 4h squared plus what? X2 over what? V1. Now, remember that what we are trying to do is simply to know which of these waves will get to the geophones first. So we are expressing these waves in terms of what time. Now we are first looking at the direct wave and the reflected wave. Now we realize that T1, which is the direct wave, was the time for it to get is given by this equation. Then T2, the reflected wave, the time for it to get to the geophone is given by this equation. So you could see that this time has been increased by a certain parameter of what? 4h squared. So it means that the direct wave, if you compare the two, the direct wave is going to reach the geophone faster than what? Than the reflected wave. Also, you can also take it from this perspective. Now I realize that the direct wave and the reflected wave are within the same material. You get it? So assuming this are F, this are D, they are within the same material. So they are going to travel in the same material or the same medium, same material or same medium. And they are going to travel with the same velocity. Now they are traveling the same medium, means that they are traveling with the same velocity, right? Now, if they are traveling the same velocity, let's consider their distance. The reflected is going to move from here to here, then back from here to here. But it's going to take a very short distance. Do you get it? And so in that case, because they are traveling with the same velocity, the direct wave, which is traveling through a shorter distance, will require less time to get to the geophone. Do you get it? So in this case, we can eliminate what? The reflected wave. Okay, so after eliminating the reflected wave, we can now look at the direct wave and the refracted wave. Now, which one of them is going to reach the geophones first? We need to find out. Now, we know that the direct wave is going to take this form, right? Now, let's take the refracted. Let me bring the refracted component out here so that we can clearly see it. So this is our focus. So it's hit here. Let me use different colors so that you can clearly appreciate it. So it's hit here. travel through this, then gets back, right? Now remember that the distance from here to here is still x. This height is still what h. Now we are saying that here is E, here is B, here is D, right? Now I can project this. At this point, there's going to be a normal. This is going to be a certain angle of incidence. This is going to be my normal. I can project it to the top. It's going to be a certain angle of what incidence. Now, because the refracted ray was refracted along the boundary, this I is my what? Critical incidence, critical angle of incidence, right? And it's the same for this side. You get it? So let me call this side J and what? H. So I have these shapes. Now, if I want to know the time taken, let me call it T3 for the refracted wave to get to the geophone, T3 is simply the distance FE, the distance the wave have to travel from F to E, divided by the velocity there, that is V1, is traveling within this medium, medium 1, medium 2. So V1 plus the distance it travels from A to B. So A to B divided by the velocity there, that is V2, plus the distance it travels from B to D divided by the velocity there, that is V1. Now, if you look at it carefully, you realize that FA is equal to what? BD. Now, if FA is equal to BD, then we can see that T3 is equal to what? 2FA over what? V1 plus what? AB over what? V2. Have you seen that? Right. Now, the reason why this became to because this and this, so this and this are the same, so I can add them, making this, right? Now, let's look at the distance FE, you know. So let me draw this. So the distance FE, right? So let me draw this. Uh, let me draw this. There's a certain angle there. Height here is h. That is my F what? FG. Now I want this distance, right? I can use Pythagoras. FA is my hypotenuse, right? So I can see that I can see that h over my hypotenuse, that's adjacent over the hypotenuse, is equal to cos of the angle. Which angle is there? Critical angle of critical incidence. So I see. And so if I want to make FA the subject, it's going to be h over what? Cos what? I what? I see. You get it? You get it? Now, if I also want AB, see AB. So from here to here, I want AB. Now, if you look at it carefully, um, I know that this distance, let me call it E. Let me call this distance B. That is from F to J is E. H to D is B. And let me call from J to H as C. Now, A will be equal to B. Do you get it? Now, we have to find what E is. So E, I can see that tan of the angle is equal to tan of the critical angle of incidence is equal to opposite, that is A over the what? The adjacent H. And so if I want A is going to be H tan what? I what? C. Now I said that A is equal to B, right? And we also know that if you look at this carefully, if you look at this carefully, you can see that A plus B plus C is equal to X, right? So I can see that H tan IC plus another H tan IC plus C is equal to X. So I can say that C is equal to X minus 2H tan what? IC. And that my C is equal to what? My AB. So I can see that AB is equal to X minus 2H tan what? I would C. So if I have these parameters, I can substitute this into this, and I can also substitute this into this. So with these things in place, we can put them here. So this is equal to our T3. So we can now see that our T3 is equal to 2 multiplying H over V1 plus what? IC, right? Plus X minus 2H tan IC over what? V2. I can separate this. So I can say that T3 is equal to 2H over what? V1 plus IC plus X over V2, right? Minus what? 2H tan what? IC over what? V2, right? Now I can say that 2 T3 is equal to X over what? V2, right? Plus 2H over V1 plus what? IC minus what? 2H. Now I can see that tan is what? Sine IC over what? Plus IC multiplying with V2. I can do some factorization here. So I can say T is equal to X over what? V2. I can bring what out? I can bring 2H out. I can also bring cos what? IC out. So here will be like 1 over V1 minus what? Sine IC over what? V2, right? Then here, I can also decide to bring, so let me continue here. So I can see that T3, coming. I can see that T3 is equal to X over V2 plus 2H over cos IC. I can also factorize Vn1 out. So if I factorize Vn1 out, I'm going to get what? 1 minus Vn1 sine IC over what? V2. So this is what I'm going to get. But I know from Snell's law that sine IC over sine what? 90 is going to be what? V1 over what? V2, right? So I can say that sine IC over 1 is equal to V1 over V2. I can substitute this into this, right? So I can say that T3 is equal to X over what? V2 plus 2H over V1 plus IC multiplying 1 minus V1 over V2. We said it's what? Sine what? IC multiplying another what? Sine IC. And so we're going to get 2 T3 to be equal to X over V2 plus 2H over what? V1 plus IC multiplying 1 minus sine squared IC. So if you clearly know your trigonometric identity, you know that 1 minus sine square theta is equal to cos square theta, right? And so we are going to say that T3 is equal to X over V2 plus 2H over V1 plus IC multiplying cos squared IC. So one of this will cancel one of this. So T3 is equal to X over V2 plus 2H over V1 multiplying cos what? IC. Now, we've gotten the equation. So this is the equation for what? Excuse me. The equation for the refracted ray. Then we got the equation for the direct. Right? Now we are going to plot them and see which one will get to the, how do you call it? The Geophone at early. But in terms of the assignment, this is what um the lecturer is asking us for in terms of the assignment. All right, so let's plot. So we are going to plot what? T against what? X. Now, if we take the first equation, if you take the first equation, you plot t against s, there is no, when you compare it, y is equal to mx plus c, is y, our gradient here is m here is 1 over v1, right? Our intercept is 0, so the line goes like this, right? Then this one, when you compare it, y is equal to mx plus c, this is our y, this is our x, so here our gradient is equal to 1 over v2, right? Then our c is equal to 2h over v1 plus what? ic. So let's assume it's somewhere here, right? So yeah, let me use a different color to make it more appealing. So this line is what? T1, which is equal to x over v1. And this line is what? T2, which is equal to x over v2 plus 2h plus ic over what? v1. Now, where T2 overtakes T1, it has a name. We call it the crossover. The crossover. So the crossover is the distance from the focus at which the refracted waves overtake the direct wave as the first arrival at the detector. So it is so in this case, it means that what it simply means that it is rather the refracted wave that will get to the geophone first. The refracted wave that will get, and this is XC, the crossover. This is where it will overtake it at this distance. It will overtake it. So yes. So basically, that's the explanation for the assignment. Thank you for watching. We'll end here. Bye bye. See you another time. I think continue. Right.